Achieving the BCNF by decomposition. Till where we have done? Okay, I think we were here, right? There is a special case of BCNF. I think we have done with till BCNF. We have resolved till BCNF, right? So we have divided it. So there is a special case. What is a special case? Like this, right? So that means if I break it, my dependency, I can't preserve my dependency. What is my main role of normal form? I have to preserve the functional dependency. This functional dependency should be retained, and there should be non-additive join property. When you join, when you after breaking, again, if you join, I should get a original data, relation state R. Data should be there. So now, in such cases, what happens? Will you able to retain a dependency? No. So how do you break it? Now, if you want to break it, two relation. If I want to go according to FD2, then my C will be primary key and B will be an attribute. Correct? If B is there, if I keep B here, then it will be redundancy for me. So that means I need to erase B here. I need to clear B. So keeping C. So if I keep C, FD2 is satisfying, that is this. But what about FD1? My FD1 is lost. Dependency is lost. So when dependency is lost, then you should take care of, there is a test for us that the dependency should not be lost. At least some dependency should be hold. So the same kind of an example I'm taking here. Fine. So that means student and course to instructor, instructor to course, dependency. I'm taking the dependency. So when you have like this, how do you have to break it? So breaking decomposition into two, you need to, because I might have different scenarios of breaking it, right? There is a chances. So which is a proper decomposition? I have a rule to be followed. So what are the possibilities that I can break? What are the possibilities? I think last class I've told you, I will use SCU. SC and SI is one table. I think these two I will make it complete because one student can take any number of course. So combination, I'll keep it primary key. One student can have any number of instructors, more than one instructors. So a combination key, primary key, according to the scenario you keep it. Next, course and student, course and instructor. This is my next one. One course should be, I think this is a combination. Any number of students can take it. So this will be a combination. One course, one instructor, actually I can make it, then I can keep it C, or one instructor to one course. Like this I can make it. Next, instructor C. This is a possible tables I can generate. This is a one set decomposition, second set decomposition. So out of this decomposition, I should know which decomposition is better. Fine. So to check that, I have a rule. A relation not in BCNF should be decomposed so as to meet this property, while possibly foregoing preservation. Most of the time we will face such problem in in a scenario of BCNF only. I have to preserve the dependency of all functional dependency in the, so I can't preserve, I should forego the preservation. Only thing I have to satisfy is non-additive join should be retained. At least that I should maintain. So there is a three possible way of decomposition I've already discussed. This, which is the better one? All three decomposition will lose FD1, correct? We have to settle for sacrificing the functional dependency preservation, but we can't sacrifice non-additivity property for decomposer. At least this we will see it. So I can decompose all this, but when I club it, I should see that, I should check that there should be no any kind of an additive or a loss of a property should be there. At least that this I should maintain. If preserving dependency is not possible, at least this I should maintain. To maintain this second one, I have a rule. A simple test we will come across in handy to test the binary decomposition of relation in two relation. Um, the name of that is NJB, that is a non-additive join test for binary decomposition. Non-additive join test for binary decomposition. Let's see what is that NJB. Okay, see now. Um, Now I have this 2D is equal to R lossless joint property with respect to functional dependency. Only when if you want to decompose anything, it has to satisfy these things. The first one is either this you should satisfy or this you should satisfy. So remember this. What is the rule? R1 intersection R2 should be tends to R1 minus R2, that should be in the at least in one of the functional dependencies of the previous table. R1 intersection R2 tends to R1 minus R2. Next, R1 intersection R2 tends to R2 minus R1. So what do you mean by that? Okay, we'll go back to the example here. Fine. See, this is my FD. Student course tends to instructor, instructor tends to course, right? This is my decomposition I have done. What is my FD? Functional dependency is, I'll write a shortcut. Student course functionally determines instructor. Instructor functionally determines, let me clear everything. Instructor determines course. Okay. Okay, let me write once again. For this three decomposition I've done. Decomposition 1, decomposition 2, decomposition 3. So now this should satisfy. Let me write a functional dependency. What is a functional dependency? Student, that was before. What was a functional dependency defined for the previous table? What was my table? The table was this. What was the functional dependency given for this table? The functional dependency given for this table was these two, FD1 and FD2. Okay. This functional dependency, let us check. So that will be FD1 was student course tends to instructor. FD2, the instructor tends to course. Then fine. So this 2 is my F plus, including all FDs, I call it as a F plus anta. Including all FDs, I call it as a F plus. That's a closure of all FDs. That's a closure property. It is F plus is a closure property. So now, what was my rule? So I'll write a rule here. What rule? NJB rule. So what was the NJB rule? NJB rule is R1 intersection R2 should be functionally determines R1 minus R2, right? The second rule was R1 intersection R2 functionally determines R2 minus R1, right? Now I should check this which is the best decomposition. How will I check? All those decompositions should satisfy NJB rule. So let me go with D1. Let me check whether the D1 is satisfying or not. Okay. Okay. So let me check now D1. So what is D1? D1 is this R1. What is the relation 1? All these are R1. All these are R2. Okay, I'll write down. All these are R1. This side is a R2. Now let me check with the rule. So what is a rule? R1 intersection R2. What is an intersection? Can you tell me what is the solution of R1 intersection R2 for D1? For D1? So only Manoj is listening to the class? Yes, common attribute, obviously, common attribute. Okay, good. So what is a R1 intersection R2? Student, common. So, student functionally determines, what is my next rule? R1 minus R2. What can be R1 minus R2? Nayana, it is a common intersection and no common attribute, Nayana. Now you tell me R1 minus R2. Yeah. What is R? Oh, yeah. What is R1 minus R2? Yes, correct. The attribute which is there in R1 but not in R2. Which is the attribute? Instructor. So write an instructor here. Write an instructor. Now just check whether this dependency is present in any one of this functional dependency. Student tends to instructor. Is that present? No, it's not present. Correct. Now I've written in the red color, right side top. So which one I should check? See, I've given a pointer now. This is my FDs, which I've given FDs for the table, which I have to check whether the FDs, what is derived from the NJB property is present in the FD set. It is not present, right? It is not present. So I can't do this. Go for the second one. For D1, first one is done. For D1, second one. R1 intersection R2 is student only. It tends to R2 minus R1 is what? Course. Do I have this FD in a given set of FDs in F plus? No, right? So my D1 is ruled out. I can't use this kind of a decomposition. Is that clear? Check D2. Check D2. So use the same formula. R1 intersection R2 is what? Course. Correct, no? Okay, if I'm wrong, you just tell me. R1 minus R2. What is R1 minus R2 instructor, right? So do I have this FD in my F plus? No. Go for the second one. This is same. Course tends to R2 minus R1, that is student. Do I have this FD? No. So D2 also ruled out. I can't use this decomposition. Fine. Next one. D3. D3, first one. R1 intersection R2. It is instructor. Tends to R1 minus R2. R1 minus R2 course. Correct, no? So do I have this? Yes, see here. My FD2 is having instructor tends to course. So that means when I use NJB property, right, or a rule, I should, whichever the functional dependency I derive here, that should be present in F plus of the given functional dependency. If I'm able to get at least one functional dependence, at least one functional dependency from the given set, then that is the one. If I don't get any functional dependencies, then that is not a better one to decompose. So that literal meaning only would have been gone. That determines, functional determine is nothing but who determines who better uniquely. That is actually defined there. If even one, if it is not satisfying, that we don't decompose it. You understood? Decomposition. Now, which is the one I have to decompose? I have to decompose this one. D3. That is instructor course and instructor to student. All this NJB is decomposition by into two tables. It's only two tables, not more than two tables. The rule is not there for more than two tables. It's only two tables. Is that clear? So the same thing you can apply for ABC to C tends to D. You can check it. So clear? Shall I clear this? Shall I clear? Okay. So that is the property here. See, that's a property they've asked. For this property, now you see, now you read this. A decomposition D is equal to R1 comma R2 of R has a lossless or non-additive, both are same, joint property with respect to the set of functional dependency F on R, if and only if either the FD, this is my FD actually, the FD, this is in F plus. If it is one of the given F plus F, or this FD should be in this F, then only I can say the D is satisfying, the decomposition, whatever you have done between the, for the two tables you have decomposed, that is satisfies. Is that clear? So what was the solution? We have done this. So we could able to derive instructor tends to course. Hence, what do you teach one? You will divide into two tables, that is teach one, instructor course, and teach two, instructor student. So this decomposition is done finally. So now you understood NJP property? Yes or no? So you people lost somewhere? Physically you are lost, or mentally you are lost, or you are lost with respect to this topic? You can tell me, I'll repeat it. Girls, I got only boys' consent here. Okay, fine, fine. Now we'll jump to fifth normal form quickly. Okay, I'll just brief the fifth normal form. Okay, give you only a brief. You can, when you read it, you will understand. It's not that simple because my main intention to go to the problems. Problems is my first concern. Okay, joint dependency. So now the point I'll come here. So when you will come to fifth normal form, when you don't get multi-value dependency, when you don't get BCNF, any problems, till multi-value dependency, everything is binary decomposition, right? BCNF, if you get any problem, you use NJB. When preservation, dependency preservation, usually you will get in BCNF dependency. If most of the case. So using NJB property also rule also does binary decomposition. Binary decomposition andre, one table is divided into two tables is called a binary decomposition. That's all. So all this still multi-value dependency, you will break the table into two, right? But what happens here when you break the table into two? When you break the table into two, you still find an additive joint decomposition andre extra rows or loss of rows that you will see. Okay, but there are some cases that when you decompose a table into three tables, one table into three, then actually you will not see any kind of an addition of the table. That is, non-additive joint property will be satisfied. In such cases, you will go to joint dependency. Okay. This directly they will give you MVD. You will get one problem I have sent you. This directly what is fifth normal form they'll give you. There is no other problems. There may be no functional dependency in R that violates a normal. So you will not have functional dependency that violates BCNF, and there will be no multi-value dependency also is found to that violates 4NF. So in such sort that there is no other dependencies, we then resort to another dependency. So in such cases, we come up with another dependencies called joint dependency. And if it is present, carry multi-way decomposition. Just check whether it is having a joint dependency problem. If it is having a joint dependency problem, then we have to go for a fifth normal form. So what do you mean by joint dependency? Joint dependency, when you divide into more than three tables specified on a relation schema, specifies a constraint on relation state R of R. So the constraints states that in every legal state R, the current state, they should have a non-additive. So when whatever you break down, there should not be having an additive join. So if you break down into two tables and you're finding an additive join, then you have to go for a three tables. That is a concept of joint dependency. More than two tables. Even in two tables, if you're finding a non-additive joint decomposition, I mean additive joint decomposition, that means addition of a table, tuples is checked, is seen, then that is a scenario of joint dependency. Fine. When you break down, you have an R1 table. This will be broken down into two tables, R1 and R2. Even after breaking this, when you try to join this, you will find extra tuples or loss of tuples. This is a called as join. So that means these are not able to join. To solve this, we need to break them into three tables, R1, R2, R3. When these three tables are again joined, then you will see non-additive property. So is that clear? So that is what he's trying to tell here. So then if you dividing the relation or tables into more than two tables, and then if you try to join it, you should get the original state, relation state R. Is that clear? That's what. So more than one table if you break. So that means two tables if you break and try to join, there is an addition of tuples or loss of tuples. Then you should go for three tables. That is a concept of joint dependency. Okay. So that's why the fifth normal form comes into picture. So what do you mean by trivial joint dependency? When you break a multiple tables, one of the tables should be equals to R. If one of the table is equals to R, then you don't have to break it. That is true, no? So that means I have one table which is equals to R, right? There will be not having any problem. So what does the fifth normal form will do? When you have a non-trivial joint dependency, when you have, so a simple rule of a fifth normal form, andre, there should not have any joint dependencies. Andre, two tables if you join, and then you get a loss of tuples and addition of tuples, then that is a joint dependency problem. So we should not have any kind of a joint dependency problem. To avoid joint dependency problem, what we need to do, we should go for a fifth normal form. So fifth normal form, directly you can say, which avoids joint dependency, which avoids joint dependency. So this joint dependency, now that what definition they're saying, non-trivial antandre R1 you have relation table. This has been decomposed into R1, R2, R2 when non-trivial joint dependency andre I have a joint dependency problem when I join these two. You need to make sure that my Ri of one relation should be a super key of R. It should be a same super key of R. So that means when you join it, it should be equal to R. Okay. So that means this is not possible. Only this is possible when you join into, make three tables and then join. Then usually your fifth normal form will be satisfied. So now, simple example. See here, there is no rule how you need to break it. You just have to break it. You just have to break it with the trial and error, so that when you join all these three tables, you should get a supply table. You should get supply table. That's why this fifth normal form is very difficult to use in practical. In practical scenario or real time scenario, fifth normal forms are not used because there is no proper, there is no, first of all, coming to a fifth normal form, that problem joint dependency is very, very, very rare. Even though if it comes, they just neglect it because they have to divide it into three. They're saying there is no rule to divide because there is no functional dependency. For multi-value dependency, you have a rule. You can go see the video. There is a rule. Based on the rule, I will do it. Multi-value dependency. But here I don't have any rule. How will I divide it? Just go with any combination of R1, R2, R3. But when you join back, see to that you should get all these tuples. You should get all these tuples. That is a rule. So that's why in this, they will not give you problem because it's completely useless for you to keep on doing a trial and error for breaking down from supply table to R1, R2, R3. When you join these two table, R1 and R2, see why they have given dotted line. When you join any of these two, either R1, R3, you will get all the three attributes. Join R1, R2, see S name, part name and project name, three you will get. Join R1, R2, you will lose this. Actually, the dot below dotted line, whatever the rows you have, you will lose that rows if you join. You join these two, again you will lose this. Only when you join all the three together, then you will get the complete rows. But which one to which combination you want to do, that is a trial and error. So that's why you will never get a problem in this. This is completely an inefficient problem. It's hardly, they say it's 1%. Otherwise, only till BCNF in a real world scenario, they will stop it. That is almost, it will achieve 99% or above 95%. So there itself, they will stop. Even MVD also, they will not do. So fifth normal form though, they will never come. Theoretically, you should know they directly give you. When they give you, please go ahead with the same example. Don't take up any new example. Is it clear? Please go up with the same example and then you write it. Very rarely they will ask this. Fine. Is that clear? Shall I go to the next one? This is all about fifth normal form. Is there any doubt? No doubt. I feel you people are, today you're not finding interest. Now you will get. So go to the recording and then you can check once again if you have not understood. Now we will go to yes, closure. Now please, I need everybody's attention. Okay, solution for the problem. Oh, sorry. Closure property. Yes, closure. I've just forgot to put the animation. Fine. Okay, closure property. Before going to a closure property, we will solve a problem. Okay, yeah. Let us consider this problem. Then I will jump to the definition. What do you mean by closure? Okay. What are the functional dependency that I have here? Please, everybody, keep your book. Start writing. There is a problems. From this on, we will have a problems. Start writing, solving the problems. Next 3 to 4 classes, we will have a problem. So this is a basic information for the problem. Take down the example first. There is one topic, inference rules. That is also is not relevant to any of the problem. I will give you a video by today or tomorrow. Okay, shall I go? Go ahead. Now what actually we are doing is we are just seeing so many methods, closure, equivalence, minimal cover, because we have already come up with a functional dependency. Who will do the functional dependency? Functional dependency is actually done by a person who actually know semantically in a depth on the uh, table, all the relation schema. They can only write the functional dependency, who would have understood better. But sometimes I can able to refine the functional dependencies, extra functional dependencies. I can understand more on the functional dependency and I can able to refine the functional dependency. For refining the functional dependency, these are all the problems for existing functional dependency, okay? So for the first concept for refining, we just need to know about the closure. So hope you have written this. Just write this example. This only this. This is just nothing but to find the closure of the given relation schema. What do you mean by closure? For each such set of attributes x, we determine the set of x plus. Any closure we call a plus symbol of attributes that are functionally determined by x based on f. Whichever is functionally determines x indirectly. Directly we know if x tends to or y tends to x, it functionally determines by y. Directly I know, but indirectly there is too many functional determinants. So let me check it. Simple one. I have just taken the simple one. What is a given FD? Solution. So given FD is A tends to B and B tends to C. So for any kind of a closure, I will start taking from the left side. I always take a closure of the left side attribute because that itself derives the other attribute in the right side. So what is a closure? Always, you please make the note. Always the left hand side attribute of FD is considered or taken for closure. It's taken for closure. Okay. A closure. First attribute, first functional dependence is left side attribute. I've taken what? A. Plus is closure. A closure is equal to always, the first rule of the closure is reflexivity. Andre, A determines A only. Now if I say Priya's group, ಆಯ್ತಾ? Priya's group andre, in that group Priya is also included. Will you exclude Priya? No, you will include Priya also. With Priya, I have other group members, right? So like that, that's my reflexivity. Always a closure will have its own attribute, right? So that I call it as reflexivity. This I call it as reflexive rule or reflexivity. Now, A can also derive from A. What can be derived? See the functional dependency. From A, what you can derive? B. A will remain from the previous A closure. B is attached. So, since A derives B, right? This is functionally determines B. Now, again, A closure. I need to take the old one. Is it clear? So I'll just write B is a new one here. B is a new one since A tends to B, right? This is my A closure. Now, AB is my old one. My new A closure is AB is an old one from A plus, right? What is a new one? B. A derives B, done. I have a B here. See, B. B derives what? C. So I can write this since B derives C. So what is my? So that means A closure can derive A, B and C. You agree? Because this is a transitive rule. A tends to B, B tends to C, then A also uniquely determines C. So my A closure is ABC. So what is a closure? So A plus is equal to ABC is my final A closure. Is that clear? Is that clear? So now I'm not done with one attribute. A, what is the one more closure I can derive? B. Right? I can derive B. So I should check all possible closures. B also. Why we need this, you will come to know further. Here only we will learn how to find the closure. Why do we need this closure? So you will come to know further. B closure. What is a B closure? The first one will be B itself. Reflexive rule. Okay? Now, I need to take for the new B plus, will B derive any attribute? Yes, C, right? Since B tends to C. Yeah, next. What is a new one? What will be BC? Can any other attribute can I derive? So BC is from the old. Can I able to derive C? From C can I, from B I could derive C. From C can I able to derive anything? No. No more attributes can be derived. This is for your reference I'm writing. So what is a closure? B closure, BC. So the final B closure is BC. So now you understood about the closure. Now, if you have understood, now read the definition. Now read this definition, you'll understand. For each such set of attribute X, we determine the set X plus, that's X closure of attributes, that are functionally determined by X based on F. What is my F here? Given FD. That is my F. Okay, I can write F only here. I can write F only here. So what is my F? Based on F. Based on F, functionally I can determine many attributes. So X closure is called the closure of X under F. A plus is equal to ABC I have got only because of functional dependency F under F. So closure of X is determined under F. So you understood the definition of closure now. Any doubt? Okay. Gautami, Kevin, is that clear? Sudeep, Nisarga, Nishant. Prashant, Pooja, I'm just randomly picking the names. Whomever I know regularly, whoever messages me. Rishabh, it's clear. Everybody is clear. Okay. So now, whatever I have done this problem, that is written in the form of an algorithm. They will ask algorithm. It's very important. So that's why before going to the algorithm, I have solved the problem and then we have gone for the algorithm. Okay. Now, input A. So just read the algorithm. You'll come to know now. Input A set. Input A, input along. What is the information input is required for the algorithm? A set F of FTs. I need a set of FTs. On a relation schema, yeah, I need one relation. On that relation, I need some FTs and a set of attributes X, which is a subset of R. Obviously, I need some of the attributes for the relation, then only I can derive an functional dependency. Now, when do you call X plus is a closure? First, X plus is equal to X. This is a reflexivity. I just forgot to write this. Reflexivity. Right? Now, this statement should be repeated. This statement should be repeated. Until what? Until this point. So now just see. This should have come this side. Okay, fine, whatever it is. Old X is equal to X plus. For each, already I have X plus here. That's why this X plus is new X plus. Old X plus is this. What will be my new X plus? For each functional dependency, Y tends to Z in F. Now I've taken one functional dependency. Do, what is a do? Is Y is a subset of X plus? Is Y is a subset of X plus? Now I have taken what? A plus alpha is equal to A. Fine. Now for A tends to B, I'm checking. If A tends to B, is A is a subset of A plus? Yes, it is already a subset of A plus. Then what you can do? X plus union Z. What is Z here? Y tends to Z. What is Z? B. If A is a subset of already in A plus, then you can add B. That is Z. So now A plus will be union to B. So what will be A plus? A with union B. That's nothing but AB. It is A union B. It is nothing but AB. Right? A union B, which is equal to AB. So what was the next functional dependency? B tends to C, right? Now, I'm done this. If, again for loop, or if old x is equal to new x. No, I'm not able to find it. Now, next one. For each function, now new functional dependency I have. Okay? New functional dependency I have. So that is, again, is y is b, is a subset of x plus a plus, yes, it's already a subset. Then z, you can make a union. A plus is equal to ab union c. Okay. Now, until when x plus is equal to old x plus, that means nothing but, now find out any functional dependency. I don't have anything. So my old, if I want to new, this is my new. Every new thing is my new. Now this is my new. This is my old. So can I able to derive again? No. So I should keep the old one only. So till when I keep the old one itself, till then I have to keep on doing the closure. Is that clear? Fine. Now let's see. Please find out and tell me what is a closure. What is a closure? Take on this example.
Ma'am, one doubt, ma'am. With respect to this question and the previous one, ma'am. In the first question, we considered A, B because A derives B and B derives C.
Wait, hold on. Tell me now. Yeah.
Yeah, ma'am. In the previous question, A derives B and B derives C. So is it? That's why we took A and B separately, no, ma'am. We did not consider C because C does not derive anything.
Yes.
So here, so example in this one, we need to consider A, B, C, D, E also.
Where is
Or
where,
I'm sorry, A, B, and D we have to consider.
A, B, D, C?
Okay, ma'am. Okay. Yeah, these four only we have to consider.
No. That is closure. If I have told all the closure, then you could have done A, B, D, C. But I've asked only a closure here. See, A plus. What is A plus? The question.
Okay, ma'am. Okay.
You just have to find me A plus.
Yes, ma'am. Got it. Thank you.
Yeah. It's not A plus. It should be always A closure. You can't tell A plus. A plus andre ಇದು ಹಿಂಗಾಗೋಗುತ್ತೆ. So this is A on top plus. So it is A closure. Yeah, that's fine. What you can't type? No, that's fine. Directly you give. Since and all you don't give. Direct answer you give me. A closure includes what all the attributes. That's all I need. That's enough. Okay, you're sure? Okay, I'm getting answer. Let's check. Okay, A closure is A. So reflexive role. Next, yes. Let me see. A derives D. So all that since and all you write. Since A tends to D. Okay. Next, what happens? A derives D, that's all. D derives B. A, D, B. D tends to B. Next, B derives E. A, D, B, E. Since B tends to E. Okay. So that's all. Yes. So my A closure will be ADBE. Fine, correct. Now my second example. Now tell me. So if I've told find the closure of all the attributes, then you have to find all possible attributes. Let me see. What are the possible attributes closure? Which one you'll find out first? Which one you'll take as a first closure attribute? Yes, take SSN. So first will be SSN closure. Tell me the answer, SSN closure. Why got confused for this? Yes, that's the answer. SSN closure is SSN reflexivity. Through SSN, you can derive what? SSN tends to E name. SSN comma E name. So this will be the closure for SSN. Now, which closure you will take up?
Excuse me, ma'am.
Yes, Sanjini.
Ma'am, we'll not consider that SSN P number to ours, ma'am.
No, the combination only should be there. If you would have had with SSN comma E name comma P number, somehow you would have got through any of the functional dependency. As you would have had P number again, with these combination, you could have derived hours. But I have only single attribute here, SSN. How will I derive hours?
Ma'am, SSN P number together derives ours, ma'am. So we can't consider it separately for SSN.
Single attribute,
Okay.
single attribute will uniquely determine hours. It is only
Okay.
uh, it is only a combination of the attribute uniquely determined. So if you have both the attribute here, then you can uniquely determine hours, but not single attribute.
Okay, ma'am. Thank you.
So yes, Nandish gave me what is the next closure attribute I'll take? Yes. P number. P number closure. So what is the answer for this? Yeah, Kevin, you should include P number also. Reflexive rule. P number, through P number I can derive P number, comma, P name, comma, P location. All the three. So that steps and all you use it. Okay. Now what is a closure property I should take? I should take combination. You can use small bracket or the flower bracket, anything. Now, can you tell me what is a closure property for this? No, Sudeep. No. Nitish also gave, Kevin also gave same answer. No, Srividya. What is a closure property? Correct, Nandesh. What is a closure of this final answer? Yes, Srividya, correct. C. SSN P number is a reflexivity. SSN comma P number. Okay. I'll take equals here. Okay. Next. These two SSN P number takes what FD? Sorry, hours. It takes hours, right? So SSN comma P number together derives hours. Is that clear? Please use the FD there and then. I am not using. Please use the FD there and then. Okay, I'll do one thing. Clear everything. I'll start from here. SSN comma P number is a reflexive rule. Next, SSN comma P number comma hours is based on since SSN comma P number tends to hours. Next, wrong, Sudeep. Why did you leave SSN and P number? Reflexive will join. No. Now I have these attributes. SSN I have. So SSN alone derives what? Ename. SSN P number, comma, hours, comma, ename, from which SSN tends to ename. If I want to use combination, I should have both attributes in the closure property. Fine. Now, SSN, P number, hours, ename, which I will add now. What I have P number, one more FD is pending. P number I am using P name, P location. So I will add P name, comma, P location. By using what FD I have done? P number tends to P name, comma, P location. So what is my final FD? This is my final, closure property for SSN, comma, P number. For SSN, comma, P number. Is it clear? Is that clear?
Excuse me, ma'am.
Yes, Sanjeevani.
Ma'am, when we see what SSN is deriving, one SSN also should be there, no, ma'am. The reflexive rule that will not get included here, ma'am. I mean, it will repeat, but
Repeating is happening. I am taking a closure property for SSN comma P number. That reflexivity I'm using here.
yeah, ma'am. So individually, when I see SSN, if I take SSN plus, I will get one SSN on the right hand side. So that SSN will not take.
Yes, I am taking that we have done. No SSN closure. SSN I'll get. From SSN I can only derive SSN comma E name. That's all.
Okay, ma'am. Okay, ma'am. Got it. Thank you.
Is your doubt clear, Sanjeevani?
Yes, ma'am. Yes, ma'am. I got it.
So now the answer is for the closure of SSN comma P number closure. Okay, I got the answer. Fine. Thank you. So I think today closure example we have done. Tomorrow we will see other examples. Yeah. Thank you. Can you tell me tomorrow afternoon you will be free? Because I have a lot of problems from today onwards. It's completely problems only. So what is tomorrow afternoon you're free? What time you will be free? 3 to 4 shall I take? At least I'll finish one variety of a problem. It's an interesting problem, seriously. It's really not boring. If you find boring, then we will just cancel. I just don't want to force you. What time you have environment class? 2 to 3, right? What time you have class, environment class? Okay. So your environment class is at 2 to 3:15. Fine. Okay. So who is at faculty? I'll just request them to take from 2 to 3 so that I will take from 3 to 4 to schedule class from 2 to 3. Shall I take from 3 to 4? Fine. So shall I? Okay. So then I can take from 3 to 4, right? You give me a timing, I'll take that timing. So 3 to 4 is fine. 3:15 to 4:15. Okay, you take. Okay, fine. Then 3 to 4, I'll do it. 3:15 to 4:15. We just want to wind up by 4:30, so it gets delayed. So I'll take by 3 to 4. Yeah, fine. Any other problem for 3 to 4? Or you can intimate to the respective madam for 2 to 3 to schedule. Or if you tell me the name, I'll just intimate her or I'll just see to that. So we will schedule from 3 to 4. Okay, it's from civil department, Shilpa MS. Okay, fine, I'll find out. Okay, yeah, thank you. That's enough. So I'll schedule from 3 to 4 tomorrow. Okay. How about on Saturday? I'll talk tomorrow. I'll talk in the afternoon. Okay. Today again, you need to attend the class. Yeah. Sorry for delaying. Thank you.